Gonna be a mighty alkene, I just need a double bond.
Well, I've never seen a functional group that doesn't make me yawn.
One bond must be a sigma bond, the other one a pi.
No, I'm not free to rotate around. My bond energy is high. Thus far, alkanes are rather boring groups. Oh, I just want to be an alkene.
Hi, I'm Simba, and today I'm learning about organic chemistry.
And I'm Rafiki, and today I'm going to teach you about alkene and alkane reactions. Before we get started, you should probably know that a hydrocarbon is a chain of carbon and hydrogens. An alkane is a saturated chain where every carbon is single bonded to another carbon. In an alkene, we have a double bond between at least two carbons. A double bond is made up of one pi bond and one sigma bond. The pi bond creates a barrier to rotation. Alkanes can undergo substitution reactions. In a substitution reaction, an electron-dense nucleophile attacks an electron-poor electrophile. The nucleophile knocks off a leaving group from the electrophile in order to form a bond. There are two mechanisms for a substitution reaction, SN1 and SN2. In an SN1 reaction, the leaving group leaves before the nucleophile attacks, forming a real carbocation intermediate. The product will have mixed stereochemistry, and this mechanism is favored by tertiary carbocation intermediates, weak nucleophiles, resonance, and polar protic solvents. In this example, bromine is acting as our leaving group, Cn is acting as our nucleophile, and this carbon is acting as our tertiary carbocation. When bromine leaves, it forms a tertiary carbocation, and the nucleophile attacks the carbocation. This is the final product. In an SN2 reaction, the nucleophile attacks the electrophile at the same time the leaving group leaves. Because this occurs at the same time, the leaving group blocks the nucleophile from one side, forcing the nucleophile to attack from the opposite side of the molecule and reversing stereochemistry. Instead of a real carbocation intermediate, there is a transition state. This mechanism is favored by less sterics, strong nucleophiles, and polar aprotic solvents. In this SN2 reaction, this is our leaving group, this is our nucleophile, and this is our final product. Notice that we reverse the stereochemistry at the chiral carbon here and here from S to R. It's important to remember that when forming a carbocation intermediate, we have to watch out for hydride and alkyl shifts. A hydrogen or a methyl group may shift over to create a more stable carbocation in a reaction. In this hydride shift, we start out with a primary carbocation. This is very unstable. So this hydrogen moves over to this carbon, and this forms a tertiary carbocation, where this carbocation is bonded to three different methyl groups. Alkanes can also undergo radical reactions. Radical reactions have important applications. Radical reactions can form polymers, and many of the products you use in your home are polymers produced through radical reactions. Free radicals also form in cells as minor products of respiration. Radical reactions carried out by antioxidants can help to form more stable species that can be excreted through the body. There are three stages in radical reactions: initiation, propagation, and termination. In initiation, creation of radicals produces a net number of radicals to increase. Applying heat or light to halogens can cause radical initiation. In propagation, there is no net change in the number of radical species. In termination, two radicals form a bond and decrease the net number of radical species. Radicals are most stable at the tertiary position, similar to carbocations. In initiation, bromine is treated by either light or heat to produce two bromine radicals. In this example of propagation, a bromine radical extracts a hydrogen from a carbon, forming BRH and a carbon radical. In this example of a termination reaction, two radical species come together and form a bond. Alkenes can undergo addition reactions in which a pi bond is removed. These are very common and most are exothermic. Addition reactions are regioselective, meaning that one isomeric product is favored over the other. Addition reactions follow the Markovnikov rule, which states that if a Bronsted acid is added to an alkene, the hydrogen will bond to the carbon that has more hydrogens already attached to it. Remember that because a carbocation intermediate forms, rearrangements such as hydride shifts can occur. In this addition reaction, HBr is added to an alkene and a pi bond is removed, forming this final product.